In this section, we're going to take a look at the concept of vectors.
Often in math, we talk about a quantity, we talk about a number, but sometimes that's not sufficient. Let's say we're going to talk about something physical. Let's talk about force. All right, here I have an object, which I'm going to go ahead and push. I'm going to go ahead and move it with let's say a pound of force. All right, now let me go ahead and do that exact same thing again. All right, same object. I'm going to apply 1 pound of force. Well, even though I've kind of done the same thing, it seems apparent to just about anyone observing that that had a different result. Let me do it again. I'm going to apply a pound of force again. And in fact, I can try 2 or 3 pounds of force, and nothing's really happening here. That's because the amount of force that I'm putting in is only part of the story. What also is under consideration is the direction in which I'm applying the force. So sometimes it's not sufficient to give a quantity. You need to give a directed quantity. We need to talk about an amount in a particular direction. So this brings us to the concept of a vector. A vector can be thought of as a directed distance or a directed value. Here I can apply a certain amount of force and I can apply it in a particular direction. Here you can think of this as a directed line segment, saying I've started from here and I've ended here, where this is the point P and this is the point Q. This is different from saying I started from the point Q and ended at the point P. So not only do I have a distance, an amount, a number, but I also have a direction. The notation for something like this can be written by expressing the starting point, the ending point, and then conventionally we put a small arrow over it. This signifies that we're starting from P and going to Q. Note that this is different from going in the opposite direction. If I started at Q and went back to P, that would be a different vector, and it would have a different notation, starting from Q back to P, like this. One thing to notice, though, is that when we talk about a vector, we're talking about a distance and a direction. Nothing really says anything about the starting point. It's simply from here to here. So let's say, for example, that I had a point over here and another point over here, and I had a directed distance between these points, starting from here to here. All right, so let's say this is the point A and this is the point B. Well, when we talk about a vector, we're measuring a distance. Okay, well, let's say these are the same distance. Granted, I drew them freehand, so it's not maybe perfectly the same, but these are meant to be the same distance. And let's say these are in the same direction. They're both going from here this way. So here I have a different starting point and a different ending point, a different starting point and a different ending point, and different designations from A to B versus from P to Q. And yet, I still have the same distance and the same direction. What that means is that the expression of this vector is independent of its location. So what that means is I have lots and lots of vectors which I could consider as being the same. If I had a vector from this point to this point, and if I had a vector from this point to this point, so long as those all had the same distance and they were in the same direction, they would all be considered the same vector. So because of that, whenever we talk about a vector, we're not actually talking about a single object. Rather, we're talking about a collection of objects. Any of these, all of these directed distances are considered to be the same vector. So whenever we have something like that, we want to move away from the concept of, oh, there's a beginning and an ending point, and rather we want to think about the directed distance as a single unit, rather a family of units. So here we could say, okay, every one of these, even though this one starts from P and goes to Q, from A to B, let's say from C to D, and from X to Y, even though they all have a different starting and an ending point, they are all considered the same vector. So we could say, okay, the vector PQ is equivalent to the vector AB, which is equivalent to the vector CD, which is equivalent to the vector XY. But at that point, it becomes a nuisance to try to keep track of which one we're dealing with. After all, they are all the same. So the notation for a vector is often using a single name. Just like a function can be expressed as the sum or difference or product or quotient or combination thereof of different expressions, or it can be expressed as f of x, a single name. Likewise, this can be expressed from its beginning and its end point. We can try to figure out exactly which of the vectors we're dealing with, or we can express all of them, the family of vectors, with a single name. Traditionally, just like x, y, and z are often used for variables, and just like a, b, and c are often used for constants, u, v, and w are often used for vector notation. However, to further drive home the point that we're dealing with vectors, vectors are written with an arrow over the top. That's because if I write x, y without the arrow on top, or if I were just to write x with the arrow, without the arrow on top, that could be confusing. It can be thought of as, okay, well, maybe that meant a variable. So here we write this to drive home the point that we are dealing with a variable. That is important, an important distinction, because there are things about variables that we can't do with numbers. For example, we can talk about not just their size, their absolute value, their distance, but we can also talk about their direction, which we wouldn't be able to do with a number. Okay, so if all of these are the same vector, anytime I mention the vector v, which one am I really talking about? Well, all of them. Well, none of them. Okay, well, again, that's going to start to get confusing. So let's go ahead and consider the following. Let's say you had my very professional mathematical ruler. This is the kind of ruler that all real mathematicians use, right? I hope everyone has bought their own. Consider the following coordinate system. Just the typical xy plane, where your two number lines cross at the origin, cross at 0, 0. Okay, well, all of these vectors are exactly the same, right? Because the distance and the direction are independent of the starting and ending point. We could have any of these, and they all mean the same thing. Well, that means I could have a vector that started right here, which meant the same as all of those. Notice that this vector starts at the origin, and it ends at some point. Let's call that point v1, comma v2. You know, you could say x and y, but we're going to say v1 and v2 for a very particular reason. Here, all of these are equivalent, including this one down here. However, since this one starts at the origin, you don't really have to worry about one of the points, you just worry about the other point, because you know where one of them started. So this one, although it's equivalent to all the rest of them, is slightly simpler to talk about, because there's one of the points that you can take for granted. It's at the origin. So whenever we talk about a vector v, we can talk about any of its representatives, but usually we're talking about this one. This is the one that starts at the origin and goes out to some point v1, comma v2. If we call the vector v, this right here, note that that is the directed distance from the origin to this point. Since one of the points, the initial point, is taken for granted, we can express everything we need to know about this vector, both its distance and its direction, by talking about its terminal point, the point on the end. This brings us to what's called the component form of a vector. The component form of a vector, v is equal to, we can take this for granted, and so we simply report the terminal point. Now, here, this is a point. But over here, we're supposed to be talking about a vector. So if I write the vector v is equal to v1, comma v2, and put that in parentheses, that's going to be saying, oh, my vector is equal to a point. It's not. A single point doesn't have a distance or a direction. What we're looking for is the distance and direction from the origin to that point. So in order to distinguish this from the point, we have a different notation. We're going to use angled brackets. Note the distinction. If I say v1, comma v2, this is a point. It doesn't have a distance or a direction. This right here is a vector. It has both a distance and a direction, namely the distance from the origin to that point and the direction from this to this. This is best seen with an example. let the vector v be represented by the directed line segment from the point, let's say initial point, let's use proper terms here, from initial point 1, 3 to terminal point 4, let's say -5. Let's represent the vector v in component form. All right, this can be done entirely algebraically. We don't need any graphs, we don't need any pictures. That being said, since this is an explanation, and since I like showing off my cool ruler, I'm going to give an illustration to accompany the example. All right, so this is something that's pretty simple to visualize, but let's go ahead and visualize it together here. We have an initial point starting from 1, 3, right about there. And we have a terminal point at 4, -5. Let's see here, 1, 2, 3, 4, 5. 4, -5. So here is our vector. It starts from this point up here, that's what we mean by an initial point, and it terminates, it ends at this other point. Okay, so this is our vector v. But remember, the vector v is not unique. There's an infinitely many vectors from different starting points that are exactly the same as this one. A vector is not a single vector, it's a family of vectors. Any one that has this direction and this distance. When we answer the component form, what we're asking for is, we want the simplest one of these, the one that starts from the origin. Okay, well, that's, we want to go ahead and find how far from the origin we need to go left, right, or up and down to make this directed line segment the same as this directed line segment. Oh, well, that just means we need to find the displacement from this point, in this case, right, and then down. Oh, okay, well, then that means that my vector v is going to equal to, all right, well, note that v1 is just the x-coordinate of that terminal point when your initial point is at the origin. Okay, well, that means how far right do I want to go from the origin? Well, that's just the difference in the x values. So here I'm going to take my terminal point, 4, and subtract away my initial point, 4 minus 1. For my v2, well, that's the y-coordinate of my terminal point. Okay, well, that just means how much displacement do I need in the y direction? How far up or down do I need to go? I want to go from this initial point to this terminal point. That's the difference in these y values from the terminal point back to the initial point. -5 minus 3. Notice that is ordered. If I said from the initial point back to the terminal point, if I did it the other way around, that's going to give me the opposite direction. Those are not the same. So here, to find the component form, we want to find, all right, start from your terminal point and then work your way back to the origin. Start from your terminal point and work your way back to the initial point, which will be at the origin. So here that's, what's that, 3, -8. That would be your component form. Visually, what that looks like is, okay, let's draw another vector that starts at the origin, and that has a terminal point at 3, -8. Okay, 1, 2, 3, down 1, 2, 3, 4, 5, 6, 7, 8. Right down there. 6, 7, 8. And when I draw that, even with a crude hand-drawn illustration here, these do at least appear to be the same vector, and in fact they are. So this vector here is equivalent to this vector here, but since this one has its initial point at the origin, we can take that point for granted and simply report the terminal point. And to illustrate that this is not just the point, but the vector that ends at that point, we write it in component form with these angled brackets. Writing it in parentheses would make it a point, not a vector, and therefore not equivalent to this vector in blue. Now, whenever you talk about a vector, it's a directed distance. Okay, well, there's two parts to that. There's a direction and a distance. All right, so what is the distance here? Well, that's just the distance from the initial point to the terminal point. Okay, well, if I have it written in component form, that's just the distance from the origin to that point right there. Oh, but that's something from algebra. That's the distance formula. If we want to find the distance from point x1 comma y1 to the point x2 comma y2, thinking back to algebra, that distance is equal to the square root of the change in the x values squared plus the change in the y values squared. It's basically the Pythagorean theorem. Well, actually, no, it is the Pythagorean theorem when you put it on the coordinate system. Right? So that's the distance between any 2 points. Okay, but when you're in component form, the distance between x1 and x2, remember x1 is 0. And over here, the difference between y1 and y2, remember y1 is 0. One of your points is 0, 0. We can take it for granted. So whenever you have something in component form, then that means that the distance from the origin to the terminal point will simply be the difference between this and 0 squared. Well, the difference between this and 0 is just this. The difference between y and 0, well, the difference between y and 0 is just y. So the distance from the initial point to the terminal point of our vector is given by the square root of the difference of 3 and 0 squared plus the difference in negative 8 and 0 squared. Those are just our components. So here, since one of these is 0 and one of these is 0, we just really have to worry about these, which we call v1 and v2. v1 and v2. This is the distance from here to here. That's called the magnitude of the vector. Yeah, you can call it the distance or the length of the vector, but the most common phrase is the magnitude of the vector. It is expressed as you write the name of the vector whose magnitude you're finding, and then you put these sort of double absolute value bars on the outside. This is read as the magnitude of the vector, in this case the magnitude of v. So for our purposes over here, yes, we found this vector. We found its equivalent in component form. Let's go ahead and find its magnitude. Okay, well, that's just the magnitude of v, which is going to be the square root of, you're going to take the first component, square it. You'll take the second component and square that. And then you'll add those two together underneath the square root. So that's what? 64 plus 9 is 73. Square root of 73. So there we go. That's the magnitude of your vector. That's how strong it is. Back in the example of me pushing this cube, that's how many pounds of force I was putting in there. All right. Now that we have a concept of a vector and some of the definitions of our vocabulary, let's be a little more formal about things. So, definition. Let's begin with a couple of vectors. Let U be a vector that's given in component form as U1, U2. Okay. Let's go ahead and have a second vector. Which we'll call V, and that'll be given in component form as v1 comma v2. It's either given in this form, or if it's not, if it's given in just 2 points, you can always put it in component form. If it's given in any other form, you can always put it in component form. So in any event, you have 2 vectors that either were given in component form or you yourself put them that way. Let's let those be vectors. And let C be a scalar. Be a what now? A scalar. In other words, just a regular number. Whenever you're talking about vectors, if you need to talk about just a regular number, like the number 2, the number 5, that's in relation to a vector, it's called a scalar. You didn't think numbers were going to go away, did you? Numbers are still here. They're just being used in tandem with vectors. All right? So here we have 2 vectors and a regular number. And again, we call it a scalar when we're referring to it alongside of a vector. We can define vector operations. The first vector operation is the vector sum. The sum of the vector, let me go ahead and do these in order, vector u plus the vector v, is simply done component-wise. This is something that you'll come to love about vectors. Just about everything you do with vectors is component-wise. Okay? This has 2 components. This has 2 components. When you say you're doing something component-wise, that just means you don't mix the components in different positions. So if you're going to add these 2 vectors, to say you do it component-wise just means you're going to do something with the first component and the first component. And then, completely separate, you'll do something with the second component and the second component. Obviously, since we're adding, it seems like the most obvious thing to do would be to add the components. Notice that u1 only adds to v1, and it doesn't have anything to do with the second component. u2 adds to v2, and those have nothing to do with the first component. For the most part, anything we do with vectors will be component-wise. And anytime you see something is component-wise in math, you thank your lucky stars, because that means things are going to be relatively simple. It's when things are not done component-wise that complications occur. So here we define vector addition. We can define the scalar product, C times U. The scalar product, yeah, that means multiplying a vector times a scalar product. Why don't you just say product? Well, because we're going to have more than one product. Because here is what's happening when you're multiplying a vector times a scalar. Okay, but what about a vector times another vector? So there's more than one kind of multiplication. There's a vector with a scalar. We call that scalar multiplication. And there's a vector with another vector. That's called vector multiplication. You might ask, well, wait a minute, are those going to be different? Well, of course. A number and a variable are different, which means that they can't possibly be done the same way. Here, scalar multiplication is the simplest of all multiplications. It's the one that you would hope all the other multiplications could be like. Multiplications? Did you say plural? There's going to be more than one multiplication after this one? Yes, we're going to have 3 different kinds of multiplications. For now, we're going to talk about the simplest one, and this is scalar multiplication, which in fact, let's go ahead and label that. Scalar multiplication. Scalar multiplication is simply done with distribution. You say, okay, I'm going to multiply this by that scalar, then I'm going to multiply each component by that scalar. So here, C times U1, comma, C times U2. And that's it. That's how we define scalar multiplication. That C simply multiplies each of those. Or in other words, it affects each component on its own. Hey, it's done component-wise. Isn't that nice? The third definition we're going to have is we're going to define the negative of a vector. And the negative of a vector is, well, you can think of it as -1 times u. And all of a sudden it becomes the same as this first one. We're simply going to multiply the -1 times each of the components. So that's -1 u1, or you can just say minus u1, comma, -1 u2, or more commonly just minus u2. And we can then define vector subtraction. Vector subtraction is the same as addition of the negative. So in other words, u minus v is the same as u plus a negative v. Okay, but since negative v is just the opposite of v's, in order to add u with negative v, you would be adding u1 with the negative of v1. And you would be taking u2 and adding the negative of v2. Oh yeah, but remember, these are just regular numbers. The whole thing is a vector, but the components individually are numbers, just like we see over here. That's a vector, but the components are just regular numbers. So here, I can do what I normally do with numbers. U plus a negative, that's just u minus. So here that's equal to u1 minus v1 and u2 minus v2, which of course, well, that does seem to be the reasonable conclusion, right? If you add things component-wise, subtraction should work the same. It's done component-wise. Right? Without taking too much time to go through all of these geometrically, we're going to just go over the very first one geometrically with a quick visual example. All right, let's see here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, let's go ahead and add two vectors together. Let's say the vector u is equal to 1, 2. Keeping things nice and simple, in component form, that's 1, 2. Which, in component form, means that it's starting at the origin, and it's ending at 1, 2. Okay, well, that's a vector. All right, now let's take another vector. Let's take the vector v. And v is, let's say it's 3, 1. Okay, well, that means that you're starting at the origin, and you're going to end at 3, 1. 1, 2, 3, 1. All right, so there are two vectors. So now how do I add those together? Geometrically, the way this looks is it's a sequential application of a force. I have an object here. I'm going to apply two forces sequentially. First, I'm going to go this way, and then I'm going to go this way. All right. Here's the origin. First, I'm going to go this way, and then I'm going to go this way. Well, you know, that result could have just been done by just doing one motion directly. So when we add two forces together, what we're doing is we're saying, okay, I'm doing that, and then I'm doing that. Oh, but by adding them together, I really just could have done one thing from the very beginning. So it's going to apply the two vectors sequentially. Meaning, okay, starting from the origin, first I apply u to take me from here to here, and then I apply v. Remember, v is not just this vector, it's any vector that has this distance and direction. So, even though this is v in standard form, in component form, v could be represented by any vector, anywhere that had this distance and this direction. So, why can't I have one that starts here? Well, if it starts here, its component form is still 3, 1, which means I go to the right by 3, 1, 2, 3, and up 1. Now, there's no reason why I had to apply them in that order. I could have said v plus u. I could have said v plus u. That would have been, okay, first let me apply v from the origin to here, and now let me apply u. Okay, well, if I already applied this force, I'm sitting right here, so now I need to go 1 to the right and up by 2. Hey, that ends in the same place. Okay, sure. I can either do this, then that, or do that, then this. Either way, I end up at this point. Okay, well, you know, instead of taking 2 steps to get there, I could have just taken a single step from the very beginning. Starting from the origin, I could have just gone straight there. Okay, well, if I started from the origin and went straight there, what would have happened? Well, I'd have to go to the right. 1, 2, 3, 4, and then go up 1, 2, 3. Okay, so this vector right here is 4 to the right, up by 3. So in component form, that would be 4, 3. Oh, but notice, that's adding the two first components gives me the first component. Adding the two second components gives me the second component. So here, that means that u plus v, 4, 3, that really just meant we're adding together 1, 2 plus 3, 1. 1 plus 3 gave me 4, 2 plus 1 gave me 3. So this is a geometric visualization, a geometric interpretation of vector addition. It's saying, okay, to find this result, all I'm doing is I'm adding the x components and the y components. Geometrically, what it's saying is you're applying two forces sequentially. First the first one, then the second one. Notice this is commutative. I apply the second force and then in the first one, I do end up in the same spot with the same resulting vector. All of these other ones can be drawn the same way, but we're not going to go too deeply into that because this is something that's a bit of a review from trigonometry. So this is just to remind us how that can be interpreted. Let's look at one more example. Here's an example done visually. Let's take a look at one more example done purely algebraically to disabuse ourselves of the notion that this has to be done graphically or that it has to take all this amount of effort. Let's say we have the vector u is equal to -3, 2. And let's say the vector v is equal to 4, 5. Let's go ahead and find the following. U plus v. Let's find u minus v. Let's find 2 times v. And let's find u minus 2v. In fact, go ahead and give that a try right now. You have these definitions. Go ahead and pause the video and give that a try. Once you have a result, go ahead and unpause and we'll go through them together. All right, so let's take a look. To add two vectors, vectors together, you're going to simply add them component-wise. So here, that would be the sum of the two first components, -3 plus 4, and then the sum of the two second components, 2 plus 5, and that would give us 1, 7. So visually, what that is, okay, first I apply the vector u to bring me up there, and then I apply the vector v to bring me over here. Okay, visually that's what it is. But algebraically, it's simply the component-wise addition of those vectors. Subtraction is simply component-wise subtraction of the components of the vectors. Here we take -3 minus 4. Remember to keep them in order, u, then v. If it was v minus u, you do it the other way around. And then here that's going to be 2 minus 5. So that would give us -7, -3. And that's vector subtraction. Scalar multiplication. U is equal to, v. V is equal to 4, 5. So 2v would be 2 times the components of the vector v, or in other words, 2 times 4 and 2 times 5, which will give us 8, 10. One thing to note about scalar multiplication is that it is exactly what it sounds like. Here, if I have the vector let's say I have the vector 1, 2. All right, so that's the vector 1, 2. All right, let's scale that. Let's say by a factor of 2. So let's double each of the components. That's the way you perform scalar multiplication. You multiply each of the components by that amount. So 2u would be what? 2, 4? Okay, well, it's 2 to the right and up by 4. Notice that's got the exact same direction. It's just longer. Okay, well then let's take 3 times this one. That would be 3, 6. Okay, 1, 2, 3, up 1, 2, 3, 4, 5, 6. Notice that is also in the same direction. It's just longer. In fact, it's the same vector in terms of direction, but this one is twice as long. This one's 3 times as long. Oh, it's changing the scale. It's scaling it up. It's the same vector, but twice as long. Or rather, it's the same direction, but twice as long. So it's a scalar multiple. We take that literally. It scales it up. It changes the scale of your vector. Note that it does preserve the direction, which will be important here in just a moment. But first, let's go ahead and do this one. Here, this is just a 2-part question. You're going to take your u minus 2v. Notice the order of operations here is still the same as with algebra. You're going to do your multiplication first, then your subtraction. Well, we already know our multiplication. 2v was this right here, 8 comma 10. Okay, so u minus 2v is that u minus that 2v. All right, so negative 3 minus that 8. 2 minus that 10. And so that'll be what? Negative 11 comma negative 8. There you go, u minus 2v. Now, hearing me talk about vectors, it does make it sound like there's a whole new breed of object here. And there is. These are not points. They're not numbers, and they're not variables in the traditional sense. They are a completely different kind of mathematical object. That being said, they are not entirely alien. They have a lot in common with just regular numbers. Yeah, they do have a distance along with a direction, which is not the same for a regular number, but that's not to say it doesn't have anything in common. In fact, many of the properties shared by a vector are shared by a regular number. So here, let's take a look at a collection of properties of vectors. Properties of vector operations. This is a theorem. So we should go ahead and state that. So normally I like to write the word theorem first, but I think, well, I can put it over here. So theorem. Not every theorem in mathematics has to be extremely elaborate or complicated to prove. In fact, many of them are really straightforward as long as you persevere through it from the definition. That's going to be one of the nicest things about vectors. Since things are done component-wise, computations along with proofs are often done component-wise. But since those components are just regular numbers, they're something we're intimately familiar with. All right? So here, I'm going to have a theorem with, this has 8 parts. We're only going to prove one of them. Our textbook proves a second one, and some of the rest of them are left to you as homework. All right? So here we go. Properties of vector operations. Let's begin with some assumptions. Let u, v, and w be vectors. Let's have a scalar too. In fact, let's have 2 of them. So let u, v, and w be scalars, and let c and d be scalars, vectors and scalars. Let u, v, w be vectors, let c and d be scalars. Then the following 8 properties are true. The first one is the commutative property. Thankfully, mercifully, vectors, just like real numbers, are commutative over addition. In other words, u plus v is the same as v plus u. So addition is commutative. Okay. The second one is, not only is it commutative, just like it is for real numbers, it's also associative, meaning I can group things however I like. U plus v plus w, I can either add the u and the v first, or I can add the u and the v and the w first, and it makes no difference. I get the same result. So here we still have the associative property of addition. The third property is that for any vector u, if we add to it the 0 vector, say the 0 vector, what's the 0 vector? Let's go ahead and a small definition over here. Definition. The 0 vector is the vector that's given by 0, 0 as its components. In other words, it's the vector that started at the origin and then didn't go anywhere, right? Has no length, has no direction. It's just starts there and ends there. It's technically different from the number 0 because the number 0 is just a single number. Here, this is a vector that just didn't go anywhere. Right? So here, when we take u plus the 0 vector, well, then that's still going to be the vector u. Just like with regular numbers, adding 0 doesn't do anything. But instead of adding the number 0, we're adding the vector 0. Note, since this is a vector, you wouldn't be able to add the number 0. Right? We don't define vector and scalar addition. We can define vector and scalar multiplication, but here, the only definition we have for addition is vector with another vector. Here, you couldn't add a vector to another number, but you can add it to another vector, including the 0 vector. So here, you still have the additive identity. 0 still exists. Okay. The next property we're going to have if you add a vector to its negative, well, then you're going to get the 0 vector. So a positive times a negative give you 0, right? A number plus its opposite give you 0. So you still have the additive inverse property. Or I'm not really going to ask you to remember these names, although you probably already know the name commutativity and associativity, yeah? The associative property is true for not just multiplication, it's also true for addition. Oop, I said that backwards. It's not just true for addition, it's also true for multiplication. So if I multiply together I guess this is a C, D, and U, that's the same as multiplying together C, D, and U, regardless of which grouping I use. I can either say C times D together, times U, or I can say D times U together first and then C. So this is also an associative property, but instead of being associative property of addition, it's an associative property of multiplication. The next property is another familiar one. If I have C plus D and I multiply it times the vector U, that's the same as taking that U times that C plus that U times that D. Oh, that's distribution. That's a distributive property. So you can distribute a scalar over a sum of, you can distribute a vector over a sum of scalars. You can also do it the other way around. If you have a single scalar, you can distribute that over a sum of vectors. C times U plus V is CU plus CV. And again, this is also the distributive property. You can distribute either the vector or you can distribute the scalar. Distributive. There we go. And finally, if you scale something, if you scale a vector by the number 1, well, then you haven't scaled it at all. Anything times 1 is itself. If you scale something by 0, well, then it's the 0 vector. Now, the proof of every one of these is done exactly the same way. They're all done component-wise. You say, well, what does that mean to do a proof component-wise? Well, in your textbook, they actually prove the associative property of addition. So they proved the second one. So I'm going to go ahead and pick another one, and I'm going to prove it, and just to give you an idea. So you can read this one as, in your textbook. And let's go with, let's do the distributive property. That's just one that we're going to use a lot, so I may as well prove it. So here I'm going to prove the theorem, just part 7. Some of the rest of these will be left to you as homework. So here I'm going to say a partial proof. In this course, we will often prove things for you. However, we won't always prove everything. Some of it is because the proofs are so similar, it becomes redundant to prove 8 different properties when all proofs are almost identical except for, oh, this one's got a plus here, this one's got a minus here. The other time where we will not prove everything is because it's beyond the scope of this class. There are some things that the result is easy enough for us to understand and use, but the proof is far more complicated. And the third reason, my favorite, sometimes it's left to you as homework. So here we're going to go ahead and do a partial proof of the previous theorem. I'm going to go ahead and prove part 7. All right, so just to restate it, C is equal to, C times U plus V is equal to C times U plus C times V. We want to prove that. All right, well, let's see here. Proof. Well, I know what these are in component form. So that's going to be C times U is equal to U1 comma U2 plus V is equal to V1 comma V2 in component form. Okay. Well, yeah, but order of operations tells me parentheses go first, so I'm going to add these together. And addition of vectors is defined for us very nicely. We can add 2 vectors by simply adding them component-wise. So I'm going to go ahead and do that. It's going to be C times. This is U1 plus V1, comma, and then I can add the second components, U2 plus V2. But now this is a single vector. Right? When I add 2 vectors together, I get a new vector. Okay, well now this new vector is being scaled. And we have a definition for scalar multiplication. You simply distribute that C into each of the components. Okay, so that's going to equal to C times that first component, U1 plus V1, and C times the second component, U2 plus V2. That's still a vector. Oh, but the components of this vector are just numbers. This is a number times the sum of these numbers. And same thing over here. That's a number times the sum of these numbers. So here I can take advantage of the typical properties of just regular arithmetic. If these are all just numbers, I can take advantage of arithmetic. I can distribute this. C times U1 plus V1 is CU1 plus CV1, comma, that's CU2 plus CV2. Like that. Okay, well this is one vector, but really it's made up of the sum of these components right here, right? And that's made up of the sum of these components right here. So really this one vector is the sum of 2 smaller vectors. The first components of one of the vectors must be CU1 and CU2. CU1, comma, CU2. And the components of the second vector must be CV1 and CV2. Notice if you add those together, that's CU1, CV1, just like you have there. CU2, CV2, just like you have there. Oh, but notice that that right there is, well, that's a common scalar. Oh, that means I could scale that out. I could factor that out. That's C times U1 comma U2. Notice the way scalar multiplication is defined, that C would multiply each of those components, CU1 and CU2. So these are the same. And same thing over here. That's a common scalar, so I could factor that out, leaving me C times V1, V2. Oh, but notice, that's just the vector U that I started with. So this is C times U plus, and that's just the vector V that I started with. But up here, this was C times, this was the vector U plus the vector V. Oh, okay. So C times the sum of U and V is equal to CU plus CV. Oh, and that concludes our proof. All the proofs are like this. You basically start with one side of your equal sign, right? You start with one side, usually the left side, but you can start with either one. Start with one side, write it in component form, and then use the definitions of addition, subtraction, and scalar multiplication to expand it out. And then Once it's all expanded out, separate it back out into individual vectors, and it'll look like the right side. Since every one of our proofs for this, for the other properties of this theorem are exactly the same, I will forego them. However, at least a couple of them will appear in your homework. So keep that in mind, and feel free to ask questions as necessary. Now, there's a few other theorems here. Which also depend on some component-wise proofs. All right, so let's consider the next theorem. Let's begin with let V be a vector and C a scalar. All right, then we have that the magnitude of CV is equal to the absolute value of C times the vector of V. All right, so that's a single theorem. Go ahead and give this a try. Just like we had this one here, which was pretty much start with the left side, write it out in component form, expand, and then separate it back out. See if you can do this. Pause the video now and give this proof a try. Once you're done, you can go ahead and unpause and we'll go through it together. All right, so let's take a look. Okay, so this is the magnitude of C times V. Okay, well, let me write that in component form. That's the magnitude of C times V1 comma V2. All right, well, I know how to perform scalar multiplication. I can just distribute that C throughout. So that's going to be the magnitude of CV1 comma CV2. Right. But I know how to find a magnitude. That was one of our definitions from before, yes? The magnitude of a vector is simply the square root of the sum of the squares of the components. So that's going to be the square root. I'm going to take this one and square it. It's just a regular number, so it's squared just the way you normally square numbers. Plus, you take the second component, you're going to square it, and you're going to stick the whole thing under a square root. Oh, well, when you square a product, you can just square each component of the product, right? Yeah. For example, if you had like 4x squared, that would just be 16x to the second power. The square would just apply to everything. Same thing over here. You could write that as the square root of, that's c squared v1 squared plus c squared v2 squared. Well, yeah, but now c2 is a common factor. So I can write this as the square root of c2 times v1 squared plus v2 squared. I just factor that out. c squared is a common factor, so I factor that out. Oh, but now when I take the square root of a product, that's the same as the product of the square roots. Multiply these together. That gives me that result. Oh, but, well, this thing right here, that's, well, that's c, isn't it? Square and square root cancel out? Well, no. It's the absolute value of c. Because if c is positive, okay, square positive, it stays positive. Take the square root, you get c again. But if this is a negative number, if you square it, it turns positive. And then you take the square root. Okay, so it's always going to give you a positive result. It's always going to give you c or negative c. Oh, okay, so then it's going to be the absolute value of c. And then this, by definition, is the magnitude of the vector v. And there's our result. The magnitude of c times v is equal to the absolute value of c times the magnitude of v. And there's our result. All right. Before, I stated that whenever you scale a vector, it maintains the same direction. It simply changes its size, its length. Well, let's go ahead and talk about something that utilizes that statement. Here's the theorem. let V be a non-zero vector. In other words, any vector except a zero vector. Let V be a non-zero vector. The vector U, which is given by the vector V divided by the magnitude of V, which is the same as saying 1 over the magnitude of V times the vector V. Right? Here, the magnitude of V is just a number. Right? When you take the magnitude, that's just a regular number. That's the length of the vector. So if you take the reciprocal, that's also a number. So this is just a scalar product. This number times V. That can also be written as the vector V divided by its scalar, by its magnitude. Those two mean the same thing. This has length 1 and is in the direction of V. So by dividing a vector by its own magnitude, you preserve its direction, but you cut its length down to 1. This is often useful when you care about a direction, but you don't care about length. That way, length is no longer a consideration. It's just 1. And since when you multiply things by 1, it doesn't change them. Right? We'll be utilizing this kind of unit vector later. That's why we use the symbol U for this. This is what's called a unit vector in the direction of V. It preserves the direction while making the distance a predictable value of 1. A unit vector in the direction of V. The proof of this one is very, very short and simple, which is very, very nice. You might try that as well. Go ahead and give it a try. Pause the video. Give it a try. And once you're done, go ahead and unpause and we go through it together. All right, so here we go. We want to find the direction of the vector V. Right? The direction. We want to find the magnitude of the vector U. Okay? We're trying to prove that it has length 1. Okay, so let's find the magnitude of U. That's equal to the magnitude of, well, that's this right here. Right? Really, all of these are equivalent to each other. So this one, if I'm looking for its magnitude, that's the same as the magnitude of this one. Like that. Okay. Oh, but we just showed that whenever you have the magnitude of a scalar times a vector, that's what this is. Remember, this is a scalar. It's just a number times a vector. We can separate it as the absolute value of this times the magnitude of this one. Notice that a magnitude has to be positive because the way we define magnitude, it's a square root of the sum of squares. That's got to be positive. Squaring that's got to be positive. Adding two positives must be positive, and the root of a positive is a positive. So right here, that denominator is positive. 1 over a positive is also positive, which means taking the absolute values just gives you what's inside. Right? The absolute value of a positive number is just itself. Okay, but now this is just a regular number, and this is its reciprocal. And what happens when you multiply a regular number times its reciprocal? You get the number 1. So this shows that the magnitude of the vector U is equal to 1. Okay, so that shows one part. It shows it has length 1. Okay, we got that. Okay, but what about the direction? Well, here, you're taking the vector V and you're scaling it. Okay, well, when you scale something, it simply stretches it out along the same direction, but has a different size. Well, yes, but if your scalar is a negative, then it'll go in the opposite direction, right? You're going to have the negative of those components. Oh, okay, so we just got to make sure that's not negative. Well, of course it's not negative. We just said the absolute value, the magnitude of V, it's got to be positive. and 1 over a positive must be positive. Since the magnitude of v, that one right there, is greater than 0. We know it can't be equal to 0 because this was a non-zero vector, so it's got to be something positive. Right? So that's going to be positive. Then 1 over the magnitude of v is positive. So 1 over the magnitude of v times the magnitude of v is a positive scaling of the vector v. So it must be in the direction of v. All right, and that shows both of our parts. It has length 1 and is in the direction of v. And that concludes our proof. This is often useful enough. We probably want to see an example of doing this. So, as a single example, let's find the unit vector in the direction of v equals, in component form, 3, 4. All right, well, the unit vector in the direction of v is equal to 1 over the magnitude of v times the vector v. All right, so let's find the magnitude of v. The magnitude of the vector v is going to be the square root of the sum of the squares of those components, 3 and 4. All right, so that's going to be the root of 9 plus 16, that's the root of 25, which is just 5. So that's going to give us 1 over 5 times the vector v. Oh, but that's just a scalar product. So I can take this 1/5, and using one of the properties that we proved, we can simply distribute this over our vector. So this will give us 3/5, 4/5. And there's our result. The vector u is equal to 3/5, 4/5. This maintains the same direction, but now has a length of 1. Finally, for this section, let's talk about the standard unit vectors. The standard unit vectors, I and j, are defined on the plane as the vectors 0, 1 and 1, 0 and 0, 1, like this. These are vectors which line up along the x-axis and the y-axis respectively. So the vector I is simply the vector that, if it started at the origin, it would go one step to the right. The vector j is the vector that, if it started at the origin, would go one step straight up. Whenever we talk about a vector in whenever we talk about a vector in component form, we give something like this, where we say, okay, here's the point 2, 3, and so this vector can be written in component form as 2, 3. Right? This is not a point, it's a vector. But the reason it's called that is because the terminal point would be 2, 3. Okay? All right, so this is one way of writing this vector. Another way of writing the vector, however, is as a linear combination of the standard unit vectors. Basically, you can take these unit vectors and just add copies of them together until you get up there. So here, I could say that's one I. Okay, let me add another I. Now from there, let me add a j, and another j, and another j. Remember, vector addition is just sequential application of a vector. So starting from the origin, I could apply I, and then I again, and then j, and then another j, and another j. Or in other words, 2i and 3j. So this vector can also be written as 2i plus 3j. While this doesn't change what that vector is, it's simply a different way of writing it. This is component form, and this is as a linear combination of unit vectors. And while that does not give us any different way of expressing this, this illustration might invoke some other thought. Note that this looks an awful lot like trigonometry. That's a right triangle, isn't it? Up to now, we've talked about a vector as a directed distance. Okay, well, we talked a lot about the distance. We've talked about scalar multiplication. We've talked about how to scale a distance down to 1. We've talked about how to find that distance. We haven't really said anything about direction, have we? So as our last thing here, note, if we want to talk about a direction, we can give it as an angle. Thinking about this as a right triangle, though, this makes things very straightforward because given this angle inside of a right triangle, I can define this angle using this side and this side. Oh, that's the side opposite, and that's the side adjacent. I can always talk about the tangent of this angle as opposite over adjacent. I can talk about the individual components. This is the side opposite. Right? This is the side adjacent. This is the hypotenuse. I could talk about them in terms of sine and cosine. Remember that if you're dealing with something that's of unit length, we're essentially back on the unit circle. Thinking back to trigonometry, as long as you're on the unit circle, let's say I have this vector here. All right, well, if I'm on the unit circle, I know that has a length of 1. Okay, so how do I find its angle, and how do I talk about this with relation to this here? The vertical and the horizontal components. Okay. Well, as long as this has the length of 1, then this vertical component is simply given by the sine of the angle theta here. So as long as I have an angle in standard position, which goes counterclockwise the way we're used to in trigonometry, this length right here, this vertical component, is simply given by the sine of the angle theta. Sine is opposite over hypotenuse, but if the hypotenuse is length 1, then it's just equal to opposite over 1. So this opposite side must equal to the sine of theta. Likewise, this horizontal component is given by the cosine of theta. Now you might say, well, yeah, but how often do I have a unit vector? Whenever you want. Every vector can be thought of as a unit vector in terms of its direction. And you say, well, what about its distance? We can find the distance and then multiply that in. If I want to find the direction of some vector that's out here somewhere, okay, scale it back to be unit in length, find the angle, and then scale it back out. That way I have the distance and the angle. What that gives us is that if you have a vector v, if the vector v has magnitude given by the magnitude of v, given by that notation, by that symbol, and the direction angle theta, where again theta is measured in the standard form that it is in trigonometry. You start from the positive half of the x-axis and go counterclockwise. Then the vector v is equal to, all right, well, the horizontal component, which is which is the first component, is given by the cosine of theta. The second component, the vertical component, the y component, is given by the sine of theta. Oh, but that would only give you a unit vector. Oh, my vector was supposed to be 12 inches long, or 16 meters long, or whatever. Okay, well then multiply by the vector's magnitude. This gives you the direction, and this gives you the distance. So for example, find the vector v whose magnitude is, let's say 6. We're not going to worry about units, just 6, right? 6 inches, 6 meters, 6 whatever, is 6, and whose direction angle is, let's say, 30 degrees, because why not? Then that means that the vector v will equal to, well, we know the magnitude is 6. That is going to scale up a unit vector whose first component is the cosine of the direction angle, and whose second component is the sine of the direction angle. Here, cosine of 30 degrees is what? Root 3 over 2. And the sine of 30 degrees would be 1/2. And so that means that our vector v must be given by, what's that? 3 root 3, comma 3. And there we go. Visually, what it's saying is, okay, you have some vector. Oh, which vector? Well, I don't know, but I can give you some information about it. I can tell you that it's got a 30-degree angle in standard position. So initial ray is the positive half of the x-axis. The terminal ray is 30 degrees away in the counterclockwise direction. Okay, well, not only can I tell you what direction it's in, I can also tell you how long it is. Oh, it's going to go forward 1, 2, 3, 4, 5, 6 units. Okay, so what's that vector? Okay, well, we can find the cosine of this angle right here to give us the first component. And we can find the sine of that angle to find the second component, the vertical component. And then when we scale that up 6 times, that brings us all the way out here to this vector. So this vector is 3 root 3, comma 3. Or if you want to write this in the, so this is in the component form. If you, however, want to write this as the linear combination of unit vectors, of course, you can always write that as 3 root 3i plus 3j. And either of these is fine. And that's about it. This brings us to the end of our section, talking about vectors in the plane. If anybody has any questions, comments, or problems, please reach out, let me know, and I hope everyone has a nice day.